Greetings and welcome. Today we will discuss about natural draught in boiler. Today we are going to derive a mathematical formula for natural or chimney draught and also a relation for the velocity of flow of hot gases through the chimney. Natural draught is obtained by the use of chimney, and this is also called the chimney draught. A chimney is a vertical tubular structure which may be made of brick, masonry, steel, or reinforced concrete, or even reinforced plastic. It is built for the purpose of enclosing a column of hot gas to produce draught. So the hot gas of combustion passes from the combustion chamber through the chimney and is discharged to the atmosphere. The draught by chimney is due to the difference in densities between the column of hot gases inside the chimney and the cold air outside. Suppose this is a system of natural or chimney draught. Air enters into the combustion chamber or furnace, and after the burning of the fuel, the hot gases passes through the economizer and air preheater, and it enters into the chimney and is discharged to the atmosphere. For this flow of hot gases all the way to the atmosphere from the combustion chamber, there must be some pressure difference. Suppose P1 is the pressure at the grate level inside the chimney and P2 is the pressure at the same grate level outside the chimney, suppose at the furnace point. So the difference in pressure P2 minus P1 is responsible for the flow of hot gases. Suppose the pressure PA is acting at a height of h, and this pressure PA is same at this furnace end and also at the chimney end, because above the chimney height this is same atmosphere, but up to the chimney height the content of the chimney is hot gas whose density is less than the density of ambient atmospheric air, and the content of the column of gas or air outside the chimney is air, and this density is more than the density of the gas inside, and this is the main cause of flow of hot gases that we are going to discuss. So this is pressure P1 and this is pressure P2. Pressure P1 at the grate level inside the chimney is equal to pressure PA, this pressure, plus pressure due to the column of hot gas of height h meters, and that is equal to PA plus WGH, where Wg is the specific weight of hot gas in kg per meter cube, and Wg is also equal to rho g, density of hot gas multiplied by g, acceleration due to gravity. Similarly, the pressure P2 outside the chimney at the grate level is equal to PA plus pressure due to the column of cold air outside the chimney, and the height of the column is h meters. So P2 is equal to PA plus WAH, and WA is specific weight of cold air, and WA is equal to rho A, density of air multiplied by G, acceleration due to gravity. So now we can find the difference in pressure. So the differential pressure dP is equal to pressure P2 minus P1, which is equal to H multiplied by difference in specific weights, that is specific weight of air minus specific weight of G. We get this from equation 1 and 2. And this differential pressure is the driving force which causes the flow of gases, and this differential pressure is called the static draught. And this difference in pressure is very small and is generally measured by a manometer, and this is called water manometer. That means U-tube manometer having water as the working fluid. Now if we use a water tube manometer, that means the content of the tube is water, and the pressure, this is the atmospheric pressure acting on the surface of the water at the right end of the tube, and at the left end this is the pressure inside the chimney, which we represented by PA, and this is P2. So this P2 minus P1 is equal to HW. We can get the reading from the U-tube manometer, and this is say HW millimeter of water. So the pressure causing the flow dP is equal to HW millimeter of water. This is the measured reading, and if we convert HW to meter, then we have to divide it by 1000 multiplied by WW, where WW is the specific weight of water, and this is also rho W into G. And value of specific weight of water is 1000 kg per meter cube, and if we put that value, dP is equal to, it comes out to be HW kg per meter square. We can express the difference in pressure in terms of millimeter of water or centimeter of water also. If it is HW millimeter of water, it will be HW kg per meter square, the differential pressure. So pressure difference causing the flow through the chimney of height h is equal to dP, which is equal to HW millimeter of water so far as the manometer reading is concerned, and this can also be written like H multiplied by difference in specific weights of air and gas. And generally the manometer reading is less than 12 millimeter of water, and this is very small difference in pressure. Now we are going to derive the formula for height of the chimney, and for that we have to assume something. The assumption is the volume of combustion gas is equal to volume of air supplied to the furnace under the condition that both are reduced to the same temperature and pressures. Definitely the volume of gas is more than the air because the temperature inside the chimney is more, but if we reduce it to the same temperature, then the volume will be same. Suppose Ma is mass of air per kg of fuel. That means if 1 kg of fuel is burned, then Ma kg of air is required or consumed. T0 is absolute temperature of atmospheric air at 0 degree centigrade or 273 Kelvin. Ta is absolute temperature of atmospheric air. Tg is absolute temperature of chimney gas, and Mg is mass of gas per kg of fuel, which is equal to m plus 1, because for 1 kg of fuel, ma kg of air is consumed. Now the mass of air ma plus mass of fuel, that is the mass of the gas. We all know that volume of 1 kg of air at normal temperature and pressure is equal to approximately 0.7734 meter cube. We can calculate it from the formula PV equal to mRT, in which P is the pressure, which is atmospheric pressure. V we have to calculate. M is 1 for 1 kg of air. R is 29.27 kilojoule per kg per Kelvin, and T, the temperature, is 0 degrees centigrade, and that is equal to 273 Kelvin. And from that we can calculate the volume of 1 kg of air to be approximately 0.7734 meter cube. Now the height of the chimney. If pressure difference is very low, the Surge law can be applied to the gas law, because P1 V1 by T1 is equal to P2 V2 by T2, and if from process 1 to process P2, P1 is approximately equal to P2, we can consider it to be constant, and in that case it becomes V1 divided by T1 equal to V2 divided by T2, or we can say V1 by V2 is equal to T1 by T2. That means V is directly proportional to T, the absolute temperature, and that is Surge law. So we'll apply the Surge law in this case, and for that VA, volume of air, divided by TA, temperature of ambient air, is equal to V0, volume of air at 0 degrees centigrade, and T0, the absolute temperature at 0 degrees centigrade, that means 273 Kelvin. Vg is volume of gas inside the chimney set, or volume of the gas at a temperature of Tg. So from this we can say the volume of 1 kg of air is equal to this much at a temperature of Ta Kelvin. From this relation we can get this, because V0 we know that is equal to 0.7734, and for 1 kg of gas the volume will be this much at a temperature of Tg. So that is for 1 kg of gas or 1 kg of air. Now if the mass is ma kg, then Va is equal to this much. We have to multiply it by ma, and if the mass remains same and temperature increases, then the volume is this much. So far we have got volume of atmospheric air is this much and volume of gas is this one from Surge law. Now we have to calculate the density of air. The density of air rho A, the definition of density is mass per unit volume, so ma divided by Va. So ma divided by this is Va, and this comes out to be 1.2929 into T0 by Ta. So this is equation number 1. Similarly, density of gas rho g is equal to mg divided by Vg. I have already mentioned mg is ma plus 1, and this is Vg. So this is equal to 1.2929 into ma plus 1 divided by ma, or we can say mg by ma into T0 by Tg. And if we put the value of T0, which is equal to 0 degree centigrade or 273 Kelvin, we get rho A is equal to approximately 353 divided by TA at a temperature of TA, that means ambient air temperature, and rho g is equal to 353 into mg by ma into 1 by Tg, where Tg is the temperature of the gas. And we can also find Wg divided by Wa, that means specific weight of gas divided by specific weight of air, that is equal to rho g by rho a. If we multiply by g, that is rho g, specific weight, acceleration due to gravity, the ratio remains same. Pressure difference dP is equal to Hw in terms of millimeter of water, and in terms of height of the chimney and specific weight is this much. Now if we put the values of Wa and Wg from the previous equations, then we get this is equal to the differential pressure dP, or delta P is equal to height of the chimney multiplied by this, and on simplification final relation is this much. So this is the relation for height of the chimney and the pressure difference dP, which is equal to Hw. So Hw, millimeter of water, or kg per meter square, is equal to this one. So this is one important formula for calculating the height of the chimney, or getting the pressure, or to calculate the differential pressure if the height of the chimney, temperature of the air, atmospheric air, temperature of the hot gases are known. Now we are going to calculate the velocity of the gases that are passing through the chimney. We know dP is equal to Hw millimeter of water. Suppose this is equivalent to H1 meter height of burnt hot gases. So in this case, H1 is called the pressure head. Pressure head H is also called, that is pressure divided by rho g. This is called pressure head. And the velocity head is, this is velocity head and this is pressure head. The static pressure required to produce the velocity of fluid is called the velocity head. And the internal energy of a fluid due to pressure exerted on its container is called pressure head. So dP is equal to, in terms of pressure head, this is Wg, specific weight of gas, multiplied by the head, pressure head, and that is equal to Hw. And Hw already we have calculated, this is this much, and if we put the value of, and this is multiplied by H1, and if we simplify it, we get pressure head in meters of burned hot gases is equal to H, height of the chimney, multiplied by this one. So this is another important formula for calculating the velocity of gases passing through the chimney. So once we get H1, that is the equivalent height of hot burned gases, we can calculate the velocity by using the formula H head is equal to half v square, and from that v square is equal to twice g h. So if we take the square root, v, velocity of hot gas, equal to 2g h. So in this case h will put h1, because h1 is equivalent height of burnt hot gases. So the velocity of gases passing through the chimney, v, is equal to root over 2gh1, assuming that there is no loss during the flow, but there is loss in the form of friction between the hot gases flowing through the chimney, and the amount of friction depends upon the roughness of the chimney material. So if there is some head loss, say the head loss in the chimney is equivalent to H1 meters of hot gas. The head, effective head or actual head is not H1, but this is capital H1 minus small h1. So we can put the new value for the head and the velocity is this one. We can say this is the actual velocity is equal to root over twice g capital H1 minus small h1. And if we simplify and put the value of g, acceleration due to gravity, g is equal to 9.81, then we will get v equal to this one. So ultimately it is k into root over h1 and k is equal to this much, which we can call the coefficient, and this value of k or coefficient depends on the material of the chimney as I have mentioned, and the value of k is 0.825 for chimney made of bricks and it is equal to 1.1 for chimney made of steel. So depending on that, the value of k is different. So value of k or velocity depends on the material of the chimney. Now, so far we have discussed the differential pressure dP is equal to HW millimeter of water, which can be measured by using a water manometer, and dP is also equal to 353H. This is our derived formula. So this is also equal to HW. One is measured value or experimental value and other one is the derived formula. And we have also got a relation for the pressure head or equivalent height of hot combustion gases H1 is equal to this much in terms of height of the chimney, mass of the air and temperature of the hot gas and atmospheric air. And V is equal to this much. This is the theoretical velocity without considering the loss. And if we consider loss, the velocity v is k into h1, where k is equal to 1.1 for steel material and 0.825 for brick material. And sometimes we can also calculate this by using this formula, 4.43 multiplied by this. In some cases, the value of h1, that means loss of head due to friction, may be given. By using that formula also we can calculate the velocity of flow of hot gases through the chimney. So by using this formula, we will solve some numerical problems in our next video. So thank you for watching.